Hi guys, and welcome to the second part of week 6. We are still dealing with week 6. We're still dealing with the solar system. And as I was arguing last time, basically, we finished planet Earth. We finished all the properties of planet Earth. We took what we learned from planet Earth, especially in terms of structure, and we tried to apply it also to the moon, because that's also an object that is tangible, an object that is within the reach of mankind. So that is an object, whether through observations or through actual landers or manned missions and so on and so forth. So that's an object that is actually within reach. And also, we're actually trying, usually we decide which one is going to be. Is it going to be Mars or is it going to be Venus? And in this case, it's really an easy call. For me, it's Venus because Venus has a lot of properties that are similar to Earth, but also has stuff that is not similar to Earth. And we want to learn from that. And we want to also apply what we know from Earth to Venus. It's a little bit kind of easier in a sense. So this is basically the whole point of trying to make all of these cases for it, okay? So let me share the screen first. Let me find it. It's unit 41. So let me go back, share. Unit 41. So basically, again, we're talking about Venus. We'll try to make some reference at some point to Mars. And Venus was an object that was from the early on, was an object that was noticed. You can see it basically either immediately in the night sky after the sun sets, after the sun, following the sun. So usually look for it in the evening in the west side, okay? So wherever you are, look west, see where the sun set, and see for the brightest star there, period, end of the story. That is gonna be Venus, okay? Usually it sets not too long after the sun sets, or in the morning, look for it in the eastern sky. Okay, and again, it's the brightest star, and that is actually it's going to stay lit until the sun comes up. Then it's going to erase all of its color. It's going to basically dominate the day the sun does. So Venus is the third brightest object in the night sky, period. It's third only to, of course, the moon is brighter than Venus, so the moon is brighter. So Venus falls behind the moon when it comes to brightness. And both of them actually fall behind the sun. So the sun actually dominates the sky when it's up, whether during daytime or even during solar eclipse, for example, when the sun is hidden. Then when it reappears again, it clears everything again. So the sun dominates the sky, there's no question about it. And then followed by the moon. The moon, if it's there, it dominates whatever. It's going to overwhelm everything. As a matter of fact, usually for observations in the sky, you really don't want to do it on a day where the moon is full. Even half moon, even a quarter moon doesn't work for you really. So you really don't want to have the moon. And if the moon is on the east, you try to look for the west. And if the moon is in the west, you look in the east. So always try to look in the opposite direction than where the moon is, because the moon's light is very big. So the third brightest object was Venus, is Venus actually in the sky, okay? Now, Venus had a significance in the past and continue to play a major role actually in today's too, even NASA's projects that are actually still ongoing, trying to of interest to it. In the old days, basically, first of all, it was believed to be probably two different stars initially, the evening star or the morning star. That's how it used to be called. Then later on, it was recognized actually to be the same star. Okay, remember, Venus is a planet, so it's not really a star, at least according to modern definition. I mean, to the definition, the way stars and planets are. Venus is a planet, but in the old days, there were two distinctions. All of them, they were considered stars. And to make a distinction between the stars that move from constellation to constellation, from asterism to an asterism, they called them planets. So really what they meant by it is wandering stars, stars that move around. They're not like the stars that are always part of the same asterism, part of the same group. Orion, for example, has that belt in it, has that two legs on it, Rigel on one side, and safe on the other side, and has two, or actually part of the shoulders, Bellatrix on one side, and you also have Orion on the other side. I mean, Betelgeuse, I'm sorry, on the other side. And it has that shield, which is made up of a bunch of stars also in it, and the extent of the arm of Orion also on the other side. So that is an asterism. I mean, that's a shape that you recognize. It's always there. If any part of it shows, the entire thing shows. It doesn't come up, apart. For example, not the three stars in the belt, all of them, one of them disappears, or the middle one disappears, and the belt now would be kind of missing star. No, it's always there. So that is what we call stars, a group of stars that retain their shape, part of the same constellation, part of the same asterism. Those are stars. Now, this stars, namely the planets, they don't stay in that group. They move, okay? They don't retain any shape whatsoever. So that's what they call them, wandering stars, and at the end, that's what planet means. So Venus is a planet, and it's actually the closest planet to the Earth. It's the closest object to the Earth after the Moon, in its closest approach, of course. So it's closer than Mars is. So in terms of interest, Venus really should be of interest to us because it's probably the least effort to get to. It's Venus is, even compared to Mars, for example. Obviously, the Moon is closer. It's only 384,000 kilometers, about a third of a million kilometers, whereas Venus is several million kilometers, because it's about 50 million kilometers. So it's far, relatively speaking. Okay. But it's closer than what Mars is. And the interest to Venus was from the get-go going, so we wanted to understand what Venus is. So there were some missions to it initially, and there were actually landers by the Russians, and immediately it was discovered this is not a good place to be. It is super hot inside. It's the hottest planet in the solar system. It's the hottest object in the solar system after the sun. So on its surface, you don't want to be around, okay? Lead will melt. So no material, basically, at least electronics that we have today, will not be able to sustain those temperatures. Just to understand, I mean, most of the electronics, the superconductors that we use in our devices, they are rated way below 150 degrees Celsius. I mean, so with temperature around 400 degrees Celsius, you're talking about temperatures that are ridiculously hot. So nothing, no electronics will work, and that's exactly what happened to the landers. So they stayed in there for a short while, and then they basically stopped functioning because the temperature was so high. Not only the temperature was high, is high on the surface, but also the pressure is tremendous, is ridiculously high. It's about 92 times the atmospheric pressure on Earth. So the pressure is high, the temperature is high, and the conditions are not suitable for life on Earth as we know it. In addition to suffocating atmosphere, mainly carbon dioxide. And that is actually also another problem for the planet. And in terms of composition, it's not really too different in terms of atmosphere from Mars, with the exception that Mars is a lot less atmosphere than even Earth, let alone Venus. And it's mainly carbon dioxide. And like the Earth atmosphere, which is mainly nitrogen. I mean, let's put it differently. Excuse me. For the most part, it's nitrogen with 20% oxygen and some traces of the other elements, including carbon dioxide. The picture is reversed for both Mars and Venus. Carbon dioxide is the main element in the atmosphere. And not only that, for the case of Venus, it has carbon dioxide and it has a lot of it. So no life as we know it will survive those conditions. Even with the atmosphere itself, it's suffocating for any life that we know it. To make matters worse, the atmosphere actually has high concentrations of sulfuric acid. As a matter of fact, it rains sulfuric acid on the surface. Obviously, the surface is so hot that the rain, which is sulfuric acid, again, not water, evaporates even before reaching the ground. So that's really how extreme the conditions are on this planet. They're so odd. Now, in terms of similarities, it's not too different in terms of size. So Venus and Earth, barely different in size. So the radius is about what, 6,400 kilometers for Earth. It's about 6,000, and let's round it to about 6,050 kilometers. So you're talking about 350 kilometers only in difference in size. So it's slightly less than the Earth. In terms of mass, excuse me, it's also very small, very close from that of the Earth, okay? Obviously, the density is slightly less than that of the Earth, and the reason for it is not big. It's not big deal to. It's not really hard to understand why that is. Although there is a small difference in radii, but this translates in a bigger difference in volume, because remember, the volume is proportional to the radius cubed. I know we did this at some point in there. It's given by the geometrical expression for the volume of a sphere of 4 divided by 3 times pi times the radius cubed. What matters in here is the cube of the radius. Objects are smaller in radius, so they don't look too different from one another, but the volume is a lot less. So because of that, the density, actually, the mass also is a lot less than the Earth, okay? The mass is a lot less than the Earth. So when you do the ratios, the density of the planet, it turned out to be actually less than, so when you plug in all of the numbers, less than that of the Earth. So in terms of composition, it's not too far from the Earth, but there are some distinctions between the two. Obviously, they form in 2 different regions, and they all evolve differently, okay? So this is, in terms of similarities, let's focus on 2, size and mass. And actually, third one that follows as a consequence is gravity. So they are similar. In terms of differences, the pressure on the surface, temperature on the surface, atmosphere, both composition and amount. And what else am I missing in here in terms of differences? In terms of differences, also in terms of geology, the Earth is really governed by the plate tectonics, whereas Venus does not have plate tectonics. Venus is actually one big block, and it has volcanoes, it has outgassing, it has all kinds of similar stuff to the Earth. So volcanoes are kind of similar, except that they are far more intense on Venus than, at least in the past, they were. Led to this kind of a greenhouse effect. So this resulted in the greenhouse effect that the entire planet is undergoing. I mean, if you were to stand on Venus, you're not going to really see the sun. You're going to see haze all the way through the surface, and that's actually the pictures that we get from it. And because it's super thick atmosphere. Another thing, another distinction between the two is the rotation. The Earth does one cycle every 24 hours, whereas this one takes months to spin. So slow rotation. Okay, not only that, but this is the only planet that is spinning backward in its own axis. If all of the planets are spinning in the positive direction, this planet is spinning in the negative direction. So this planet is spinning clockwise, whereas everybody else is spinning counterclockwise. Make an exception for Uranus too. Uranus actually is spinning upside down, okay? So those are but everybody else is in the same direction. So some of these things, when you see something kind of odd, you really need to explain it. Where is that coming from? Same thing with the case when we were talking about the moon. The moon of the Earth was we noted that it's an odd exception to the rule. The rule is inner planets do not have moons. The Earth turned out to have a moon, not only a moon, but it's a big moon. So we needed to understand where that came from. Same thing in here. Venus is spinning backward, so we need still to understand. So it's still really a puzzle. We really don't have the full answer exactly to it. But again, we believe that those early collisions is probably one of them caused the planet to spin in the opposite direction. So it sustained a major collision in its formation when it formed immediately. Otherwise, it should have spun like everybody else in the same direction. Okay. So again, Venus is only slightly smaller than the Earth, but is where the resemblance basically stops. That's the end of it. It has thick clouds completely obscure the surface, so you cannot see the centers. Now, with radar penetrating technology, we can actually see to some extent the surface, and we have actually a kind of the topology of the surface of the planet. So we have an understanding of how it looks like, in other words, the lowlands and highlands and so on and so forth. It rotates very slow, once in 243 Earth days. There is a homework assignment, and the homework assignment deals with this very same issue. It's 243 Earth days, but actually, when you count for the planet that is actually moving in the positive direction still, so the cycle actually repeats only internally about half that. So it's not exactly a full year. So again, please refer to, I think, the second problem from the homework assignment to understand what this is. So the surface is tremendously hot. That's basically a lot of differences between it and the Earth when it comes to that. The atmosphere is 100 times more massive. It's actually, yeah, so the pressure is about 92 times more than the Earth. So if you were to stand on the surface, you'll be crushed under the weight of the atmosphere itself. Obviously, you have other problems to deal with. You can stand on the surface because of the heat, okay? The temperature is high. And not only that, but also because you have all kinds of other problems that you're gonna run into with the acid rain and carbon dioxide and all kinds of problems. So when we say acid rain, it's really acid rain, not like in here, which we call it acid rain. And it is dangerous and it is devastating and it destroyed a lot of trees and forests out there. But it's a lot tamer than that of the planet because it rained the sulfuric acid. And if you know a little bit of chemistry, this is what sulfuric acid look like. And this is a highly, highly acidic, it's the highest acid that I know of that you can think of, that you can imagine, okay? Sulfur and oxygen and hydrogen combined, so it's really a devastating thing. It's mainly carbon dioxide, as I was saying, okay? On Earth, it's 78% nitrogen and 20-point-something% oxygen. And the rest, which is about less than 2%, actually, because oxygen is slightly more than 20%, are all of the other elements, including carbon dioxide, water, and other gases, basically argon and other gases in the atmosphere. So that's basically how the atmosphere on the Earth is. So combined, 98% is these two elements, and the rest are the other two elements. Whereas in here, it's mainly carbon dioxide. So carbon dioxide, which is traces in here in our atmosphere, is really the dominant thing on Venus. And that's the same thing, by the way, for planet Mars too. It's carbon dioxide on Mars too. With the exception that Mars' atmosphere is a lot thinner than even that of the Earth. A lot less dense than that even of the Earth. Okay. Thick clouds of sulfuric acid, that's how the chemical composition for it. Traces of water vapor in the atmosphere. And it has lightning detected, but there is no rain. So lightning, because you have clouds rubbing against each other, so static electricity builds up and discharge happens. So that's really what that is. So it can happen not necessarily because of the water in the clouds. So that's what we believe, that the planet actually underwent a greenhouse effect. So the motion in the equator is because, again, the South Pole or the North Pole in this case, they have this motion due to the sun's heating the atmosphere. So the upper atmosphere is actually receives heat from the sun, and underneath also is receiving, it has heat from the planet, and the radiation is hitting the atmosphere, and that creates vortices. That creates like the motion of the air in the atmosphere. So again, the air rises, and as it rises, it needs to fall somewhere. So it rises from the equators, and it's going to fall somewhere, and it's going to fall in the equators in here where there is less radiation being received, and that creates those cycles, those cyclones in here, and the atmosphere is super fast on the planet in here. Okay. Although the planet itself is spinning a lot slower. So that Coriolis force that causes all kinds of hurricanes on Earth in here is not that big of a deal in here because the planet is spinning so slow. Again, this is the Venera project in here from the Russians. This is the lander and the actual surface of the planet and how it looks like. The metal that you see in here, they're actually part of the lander itself, part of the Russian lander itself, okay? And then the surface is baked, and that tremendous heat in there that can reach 750 Kelvin. 750 Kelvin will take away about 200. So it's about 500 Celsius, actually, almost 500 degrees Celsius. That is tremendous temperature, okay? That is a ridiculous amount of temperature. As I said, with the exception of the sun, this is the hottest object in the solar system. And this is volcanic rock. So it suggests that the surface is really undergoing all kinds of, at least undergoes all kinds of volcanic activity on the surface, okay? Again, the mapping of the surface using radar technology with the new missions, basically, that penetrates the atmosphere using radar technology. Radar technology uses long wavelength, and wavelength just long enough, basically, to be able to penetrate the atmosphere and gave you this picture of the surface of the planet. The surface of the planet is mainly the same, basically, level for the most part, but it has some high regions in it that looks like continents. But if you really compare them to the continents of the Earth, they're less high, less basically elevations than that of the rest of the planet. This is not water, of course. This is just lowlands and highlands on the planet, planet itself. With the exception of Maxwell Mounts, which is the mountains near the northern, basically, pole, the north pole of the planet, all of the other lands and lowlands, they're given actually women and deities and women, basically, names and all kinds of things. That's why the entire planet is actually named after a goddess. So that's basically how this is the convention, basically, that was adopted, okay? So this is just to give you an idea. Again, there is another problem also in the homework assignments. It's not just the rotation of a planet. It's actually the homework assignment basically tells you to take the following. We know how much carbon dioxide is in the atmosphere of Venus. Take how that carbon dioxide and think of a process. Let's say it doesn't matter which process it is, that somehow you can break the carbon dioxide and the oxygen out of it. So if you know the mass of the carbon dioxide in the atmosphere of a planet, which is the main component of the entire atmosphere, take the oxygen off of it and make water out of it just by bringing enough oxygen to mix the two, and now you have water. Now, if you have water on the surface, then the planet is probably cold enough to, if you do something like that. So think of this process as sort of a terraforming of the planet. How high or how deep the ocean that is going to form on the planet is going to be. And the assumption in here is that the water will go throughout the entire planet through evenly, because of the fact that, as I was saying in here, there are very few low highlands compared to the entire planet. So that's a reasonable assumption that basically the water will spread itself evenly. So again, since you know the mass of the carbon dioxide in the atmosphere, you can take that and do it to the ratio of the mass of the oxygen in that carbon dioxide versus the entire mass. And from here, you're going to find out exactly how much mass of oxygen we have. And if you know how much mass of oxygen, you will know how much mass of water you're going to have. If you know the molar mass of hydrogen, which is 1 gram per mole, and if you know the molar mass of the oxygen, which is 16 grams per mole, and if you know the molar mass of carbon, which is 12 grams per mole. So if you know all of that, and that is given to you, by the way, you really don't need to take chemistry or get involved with a lot of these things to know what that means. If you know those numbers, then you should be able to come up with a mass of water that forms. Knowing the density of water, at least under normal temperature conditions and pressure conditions, is 1 kilogram of water per liter. So if you know the mass of the water that forms, how many kilograms of water, basically, you know how many liters of water that you end up with. If you take that water and you spill it throughout the entire planet, obviously it's going to go through the entire surface of the planet. And if you know the surface of the planet, which is again a geometry that you will need to solve that problem, which is 4 pi r squared, where r is this diameter of the planet. Remember, r for Venus is about 6,050 kilometers, okay? Again, you have to convert it into meters to get the numbers in meters, okay? And so this is basically the radius of the planet. You square it, you multiply it by 4 pi, you find the surface. So now you know how much surface it's going to spread on. So this is the area the water is going to spread on. You need to know how deep the ocean is going to be in order to correspond to the volume of the water that you're going to spill on. So you multiply that height, or that depth in this case, times the area that forms from the entire surface, and you should equate it to the entire volume of the water that forms, because the water that forms, you know, its mass, you know, its volume, because you know its density. So this is the density. So once you have that information, you should be able to find how deep the ocean is. You will find out that it's going to be about 1 kilometer at most, a lot less deep than the ocean here on Earth, which can be at some points about 11 kilometers. Just to give you an idea of how much water we have in that. As a matter of fact, we can compare that to the water on Earth, and you will see it's a lot less water than you might think. So yes, it received water when it formed, but not as much as the Earth did. Okay, so the Earth had more water in it, even with equal conditions. Venus, for the most part, up to about 150 million years or 500 million years, according to current studies, did not look the way it looked today at all. It looked like more of what this picture shows. As a matter of fact, it was probably a high lands that looked like ocean, like continents, and then ocean of water in there. The planet was hotter than the Earth. The reason is because its proximity of the sun, but only by a few degrees, not that really to cause it to evaporate all of its water. Now, something must have happened to it to put it in this condition. And that is, most likely, it was a subject to an impacts, and those impacts basically caused all kinds of, caused mayhem, because the planet did not have plates like the Earth did. Because again, it's spinning so slow that there is no motion of the individual parts, but the entire thing is just becomes one solid crust. But there is a problem now. The underneath surface is still has the same amount of matter as the Earth is. So when it differentiated and it started to come closer and cool it down, the inside retained some of that relic heat, the heat from when this planet formed, just as much as the Earth did. And it needs to get rid of that heat. And Earth has a way of doing it through volcanoes and through earthquakes and through also, and that's another important thing, the motion of the planets as they move. I mean, the plates, I'm sorry, as they move. So one plate will go underneath another plate. So the plate tectonics helps actually dissipate that excess energy. So there is a subduction, and there is also, when they separate, it gets rid of that heat in the middle of the oceans. And the Earth is actually regulating itself inside by getting rid of that excess heat using this means. There is actually the convection in the mantle itself. And that convection takes heat from where the core is hotter to the upper surface and basically dissipates it over time through conduction, but mainly actually through the convection process. And that convection process at the end ultimately will get rid of that excess heat, and the planet is cooling down. Another source of heat other than the relic heat is the fact that you have radioactivity in both planets. So both planets are producing heat on as time goes by on their own without even that original heat. So again, they need to get rid of that excess heat. Earth has a way of doing it, and the plates help a lot. Venus does not have plates. So how would it do it? So the belief is, and the theory is, that at some point planet Venus was hit by probably several big meteorites that triggered volcanic activity, okay? And the flow of the magma from the entire surface to get rid of that excess heat, just like the Earth does. And that produced more gases in the atmosphere than what the planet has. So those gases now retain more heat from the sun, because heat comes in from the sun, goes to the planet, that heats up the planet, and it comes actually in the form, not heat, it comes in form of other radiations also, the visible light. It goes to the planet, heats up the planet, but Sorry about that. Anyway, for some reason, the internet froze again. So the point being in here is that the planet needed to get rid of that heat. And now after that impact and those volcanoes that released tremendous amounts of gases, those gases actually at the end of the day retain more heat, okay, and a runaway greenhouse effect, and that caused the planet to warm even more and more. So the buildup of that caused whatever water there was on the planet to evaporate. That's not enough. The water itself actually is a greenhouse effect too. I mean, can lead to a greenhouse effect too. So it's a greenhouse gas too. So the process gets accelerated in the process. So the planet gets hotter and hotter to the point that even the water itself starts to break down into oxygen and hydrogen. So you have a hydrogen gas that formed and oxygen gas that formed. Hydrogen is a lot lighter than oxygen. The molar mass for hydrogen is 1 gram, whereas the molar mass for oxygen is 16 grams, okay? With a ratio of 16 to 1. Now, the planet is super hot at that point and getting hotter by the time because of this effect. So whatever gas you have in there has started to move fast, okay, because of the heat. There is a law, one of the laws of nature, which is the thermodynamics, is that relates temperature to kinetic energy, basically, how fast the particles are moving. The hotter the temperature, the faster the particles in the air move. And that led the hydrogen especially to escape the planet for the most part. Okay, some of the hydrogen combined with other elements in there and form other materials, but for the most part, the hydrogen was escaped. The oxygen also, part of it also escaped. A lot of gases actually escaped because of that high motion. But remember, the planet is big. It's the same size of the Earth. So it retained most of its atmosphere, at least the heavy elements like the oxygen and carbon and all of that. Now, those things had to go somewhere. So the carbon and the oxygen formed carbon dioxide, more and more of it. And now the planet getting hotter and hotter. So you have a process that is really started to build up over time. And now it reached an equilibrium where all of the rays that come in, they get absorbed, send it back, so try to send it in the infrared region, it bounces back. The temperature really is extremely hot in its surface. So the volcanoes that the theory basically goes were triggered by some sort of a collision, were too many, a lot of them, and they get rid of that, and they produce those gases. And again, the planet wants to do what the planets do, and any object does, trying to get rid of that excess heat, and that is one way for it did. And that's what led to the planet the way it is today, that it is in some sort of a hot conditions. Unlike the Earth, which escaped this fate because of the fact that it had plates, and those plates really helped it, in a sense, have a way of getting rid of that heat without really going through this drastic process. Now, one of the things that is going well for the Earth also is the fact that it's spinning fast enough and basically has this property that caused it to basically get rid of also all kinds of things, and the atmosphere actually in it is retained. So it's really a lot of good things happening for the Earth, including the moon that helped to actually stabilize its motion too. So Venus does not have a moon. So that's basically in a nutshell what the story is with the planet Venus. So let me try to go back into my notes in here, share. So these are the surface features in here. What you see in here as some sort of lava domes on the surface itself, okay? And you have also lava channels that formed on the surface and the volcanoes. Again, we don't really honestly have at this point direct evidence for active volcanoes on the planet because, again, those thick atmospheres are very hard to look through. But that's basically what we have at this point. Either they happened not too long ago, or they happen from once in a while because the planet somehow has to get rid of that excess heat. Okay. In terms of inner structure of the planet, we believe, again, we are taking these things and basing them on what we know from the Earth. So again, this is what probably it looks like. Again, it has a core that is, again, iron nickel, some sort of a combination of the two because it went through similar stuff like the Earth does. It has also silicate mantle, just like that of the Earth is, and it has this is its diameter, about 6,050 kilometers, 6,052 kilometers. And it has basically no magnetic field, although the core must be hot must be probably also has some sort of a molten part of it and a solid part of it, similar to that of the Earth. And if it were to move, it's going to rub against each other, against one another. And both nickel and iron are magnetic materials, so they're going to produce a magnetic field. But the planet does not. So why is that? Probably it's because of the slow motion. Because in order to produce a magnetic field, you need two things. You need the current, electric current, and of course, you need the metal and you need motion to produce a current. So metals, in this case, you have iron and nickel, and the motion, in this case, is that of the planet moving fast enough to present some sort of a decent electric current, and it does not. So that's why probably it does not have that, which means that there is another problem. If you don't have magnetic field, then there is no way for the planet to protect itself from any kind of radiation that hits the atmosphere. Now, the planet actually has a thick atmosphere, which actually helps, in a sense, to protect whatever you have inside. But don't forget, you have all kinds of terrible conditions on its surface. So again, this is actually something that you really need to remember when you come time to do your homework assignment, because of the fact that how the planet spins on its axis and how it's going to go around the sun. Again, it's going counterclockwise like everybody else, but it's spinning with the clock. So if you are at noon looking at the sun, and the spin now is extremely slow, of course, but by the time you reach this point, the planet would have, if it were in here, if it were in this position, it's going to take you from here to here, from noon to noon, for going from noon to noon, 243 days. But you don't need to go 243 days to complete a day, really, because of the motion around the sun. Let me explain this point. Noon is when the sun is above your head, correct? So now I'm looking at the sun. If the planet spins just half a rotation right here, but I'm in this position now, I have a full day. So the actual day on the planet is not, at least the day, the day that as we know it, is not 243 days, a lot less than that, okay? So again, because of this, but it's moving so slow. So again, from noon to midnight to noon again, that is a half year. Imagine yourself on Earth. A day takes about a half year on Earth, okay? It's going to be a long day. So this slow rotation and the backward rotation combination yields to an interesting problem that you guys are also dealing with in the homework, namely the planet only gives us one phase every cycle. And what you do in this case, you take this cycle, the actual rotation of the planet as it goes around the sun, and the rotation around this axis, and that of the Earth, and you will find perfect ratios in some sort of a harmony, in some sort of a the word in here that says I'm trying to put together is the synchronized, basically. There is a word, resonance, that's the word. Resonance that puts the planet facing the Earth, or usually at the same time. Okay, I did not share with you today what is important. Actually, you guys know you have all kinds of messages. So hopefully you guys, let me go into the models in here before I share them. And let me go to model 6, because we have interesting things that we have actually. Let me go back into sharing model 6. I'm sorry, that's not your class. Sorry. So that's not your class. Let me pull the class again. Yeah, that's the one. Okay, so share model 6 now. That is the one, yes. Okay, so we completed units 39 and 41. There is this simulation from unit 39 for the moon, how it was created. And also you have a quiz. Please take care of that quiz. Okay, it's very important that you do that. You have other assignments too. One of the things that you have this week also, and I know I mentioned it last time, is you have the lunar observation. Let me open the lunar observation in here. So what you have in here, you have the lunar observation. This is your second lunar observation. You're supposed to go on Sunday, actually, the 16th, and look at the moon. Once you find the moon, then you're going to plan your day, your actual observation day, which is on the 17th, the same day when we have our next time when we meet. But you're going to go at night or early in the morning, whenever you're going to decide based on the day before, when is the moon visible, and you're going to go and document the moon position. Now, according to the weatherman, this weekend is going to be rainy. Actually, the rain, I was looking at the news early in the morning, is going to hit us on Saturday. There's something unusual for California. So we're going to have Saturday rain, and potentially they said it's going to extend till Sunday. So what that means is most likely the rain is going to end up sometime midday on Sunday, okay? So which means that even on Sunday, you should be able to do your observations. If for some reason that night, we're supposed to do the planning, is inclement weather, in a sense there's clouds and you can see nothing, then you still have the 17th, which is the actual day observation. They're calling it for a clear day. So I hope that everybody will be able to do their observations at least on Monday, October 17th. If for some reason that is not possible, I seriously doubt that there will be a problem on Tuesday, because usually your observation on one day, you do an observation before and observation after. If in case none of the others work, then you still have the Tuesday, October 18th. Now, if all fails, then that's basically what you're going to put in your report, that this is basically what happened on those days. But you're not going to go to Wednesday and then start looking for it on other days. So that's basically the point that I wanted to make sure that you guys are aware of. You have a homework assignment, you have these quizzes and discussions from before. Please take care of these things and make sure that you have them already. Okay, let me click on the homework assignment because I mentioned it several times today, okay? And I probably will do something later on to follow up either with a posting or something on how to do this problem, because you have 1, 2, 3, 4, 5 problems, and they're all interesting. I talked today about this problem, specifically the one for converting carbon dioxide into water on planet Mars and planet Venus, I'm sorry, and seeing how much we have of water that we're going to form. So what it tells you here is that this is the mass of water, I mean, mass of carbon dioxide in the planet Venus. And we want to do is, if we were to convert it into water, how much water we're going to get, basically. Okay. They tell you, note that the atomic mass of hydrogen is 1, the atomic mass of carbon is 12, and the atomic mass of oxygen is 16. And that's interesting because in the ratio here of forming carbon dioxide, I will need 2 times 16 for oxygen, plus 1 times 12 for carbon. So that is 44. 2 times 16 is 32, plus 12, that's 44. So the ratio to make carbon dioxide is 32 out of 44. So 32 out of 44 is this many oxygen. So I know how much oxygen there is actually in terms of mass. All I have to do is take 32 divided by 44 and multiply it by this number. And now I know how much oxygen I can extract off of it. But then I need to form water. Since I know how much oxygen I have, and this is how much water we will have. We will have, in the oxygen, you have 16, and the hydrogen, you have 2 times 1, which is 2, for a total of 18. So 16 out of 18 is oxygen in this water molecule. So then 16 over 18, but I already know how much oxygen I'm bringing to the picture. So all I have to do is multiply it by 18 and divide it by 16. Now I have a number for how much water I have. So 18 divided by 16 times the mass of the oxygen that forms from here, which is 32 out of 44 times this number, I get me how much water I'm forming. Since I know how much water I have, and I know, then I know how much water I have. So this question is done. Compare that to the Earth's mass. So once I have a number, an amount of mass, I divide it by the amounts of of water on Earth, I will find the ratio. I will find that this is actually a fraction of the ocean, a fraction of the water that is on Earth in here. Okay. Anyway, so basically I will know how much water I have, so I do the ratio of these two. Okay, so let me share the screen again. So based on that number, if I know the density of water of 1,000 kilogram per cubic meter, and I already found from the previous version how much water we have, then I can find what the volume of that water is. Okay, I know how much volume of the water is. I know the surface area, which is 4 pi times r squared, and r is just 6,052, if you like, 6,050 kilometers. Don't forget to make it into meters. So you have to multiply it by 1,000. You square that number, you multiply it by 4 pi, and you find the surface area. It's like taking, for example, a bottle of water and spilling on a surface, on a container, for example, on some sort of a cookware or something, a flat surface. And how deep it's going to go, it depends on how much water you're going to have. If you just take a small bottle of water, it's barely going to have any thickness. But if you take a bunch of water and you dump it in there, it's going to have a deeper thickness. So it's the thickness of the water times the surface area should be the volume that you have found from this, by basically taking 1,000 of that and making it into cubic meter. In other words, divide this number by 1,000. You're going to find how many cubic meters there. But that surface times the height, I don't know what the height is, but I can find it just by dividing the entire volume by that height, by that surface area, and I'm in business. Okay. Using Kepler's law, describe the planetary orbital sizes of the Earth as 1 to that of the Moon. So this problem is actually a sending a laser and coming back with a laser. The speed of light is 299,794 or something meters per second, or 300,000 kilometers per second. 299,000 kilometers per second, not meters per second. It's 299 million meters per second. Okay. Anyway, so we know the speed of light as it goes up, laser when you send it back and forth. So don't forget to multiply that distance by 2, or divide that time by 2, because for the laser to hit the planet and come back to us, half of that time is just spent going through that distance, and the other half spent coming back to us. So so we know the time, we know the speed, we can find the distance. And if I know the distance, that should be the difference between that and 1, because the Earth is 1 astronomical unit from the sun. Deduct from it 0.723 for Jupiter, for Venus, and then I have the distance between the Earth and Venus in astronomical units. And compare that to kilometers, and now I can find the ratio of those two numbers. I can find how many kilometers are in an astronomical unit, but now using a precise measurement. You guys understand? So here is the idea. Can I write on the screen or not? I don't think I can draw. Anyway, the point in here is, let me probably take my notes in here to explain this point in here so that you guys understand what this problem is looking for. I need to share the screen first. Share. So here is the idea. So you have Venus here, you have Earth here, and you send a laser beam, and the laser bounces back. And it takes time, which is 276 seconds, or 200 and I didn't memorize the number quickly here. 276 seconds, yes. Okay. Half of the second of that time is just spent going up. So it's 276 seconds divided by 2. That is the time for it to travel to Venus on that distance. Well, this distance is 0.723, and this distance is 1. So 1 minus 0.723 is going to be equal to, let me make sure the number is correct also. I know it's 0.7, but I just want to make sure it's 23. Yes, it is. So now all I have to do is deduct 1 from this. So 1 minus 0.7, so it's at 0.2. Okay, my brain stops functioning. So 7 in here, 7 in here, and 2.277. 0.270, yes, 0.277 astronomical units, okay, AUs. But you can find this distance in kilometers. All you have to do is take this time and multiply it by the speed of light, which is you can take approximately to be 300,000 kilometers per second, okay? If you do this ratio and multiply them by themselves, you're going to find that this distance in kilometers is this many number, but it's going to be in kilometers, and like this one, which is in astronomical units. Obviously, this is this many kilometers. For one astronomical unit, it's going to be a different number. For one astronomical units, it's going to be about 150 million kilometers, so 1 AU. But I know 0.277 AU is going to be whatever you find in here. So this is this number, what you find in here. So all you have to do is divide this number by this ratio, and now you're in business. So you could say one astronomical unit is going to be this number divided by this ratio. And now it's going to be in kilometers instead. And then you compare that to the known value, or at least the accepted value is 150 million kilometers. So it should be not too far from 150 kilometers, 150 million kilometers. So that is this problem. Let me still continue discussing this problem. Quickly share. Did I lose the page already? Okay, let's go back, share. More. It's this one. Yes, okay, so we discussed 1, 2, 3. Venus and Earth make their closest approach to each other, inferior conjunction, unit 11, every 583.9 years. Days, I'm sorry, days. Use a diagram like the one on the picture that we showed to show that nearly the same side of Venus faces Earth at each closest approach, okay? You have to know the day on Venus is, which is what I gave you, but then you have to know the rotation, and from there you're going to find the cycle and divide that by the Earth's rotation, and you're going to find the ratio is always in this simple ratio in here, okay? That's the resonance I was talking about here. Earth covers about 1 degree per day in its orbit around the sun. That's simple, okay? That's because you have 365 days in the year and you have 360 degrees in a circle. So it's roughly 1 degree per day, slightly less than 1 degree per day, okay? What is it? Yeah, because it needs to cover 360 degrees in 365 days, okay? So it's about 1 degree. Let's take it 1 degree for a moment. If Earth spun in retrograde direction, like Venus, so if, for example, the sun, instead of rising in the east and setting in the west, the sun rises in the west and sets in the east. That's basically what they're saying. In retrograde like Venus, but it still had the same sidereal period of 23.56. So it still went through 23.56. How long would the solar day be? Well, it's going to meet the sun just before, just like what happened to Venus is before its sidereal motion. That's what we were talking about in here. So let me explain this last problem in here. Let me share again. Here is what they're saying, okay? This is Earth, this is noon, this is the sun, okay? The Earth is spinning counterclockwise in 23 hours and 56 minutes. Obviously, right now it needs 20 extra minutes because it's spinning counterclockwise and moving counterclockwise, okay? So at some point, after it does a full cycle, after 23.5 hours, it's not really pointing to the sun at noon, but pointing away from it. So it needs that extra 4 minutes to point back into the sun, and then noon becomes noon again. So that is 24 hours. So this is 23 hours and 56 minutes, okay? 1 day. But now what we're saying in here is that it's spinning backward. So here is the picture. So here is the sun, here is the Earth. So instead of going counterclockwise, it's going clockwise, actually. So think about it for a moment and see what happened just short of. And now it's spinning this way, okay? So this is after 23 2.5 days. It's going to point again exactly to the stars. So 23 hours and 56 minutes, it's going to point toward the rest of the skies. So just before that, about 4 minutes before, it's going to actually be pointing toward the sun. So the day should be 23 hours and 52 minutes, roughly. Okay. So this business of 24 hours does not exist. As a matter of fact, if we define this one as 24 hours, the Earth will show an actual rotation slightly bigger than that, about 24 hours and 4 minutes. Okay, I hope this makes sense. As a matter of fact, this is an answer to the problem. I hope this whole set makes sense to you guys, and you guys understand what's going on with this assignments. Don't forget your lunar observation for this week, because again, there is a potential for inclement weather, so that you do your observation and record them as you're supposed to be doing. Thank you guys for your attention, and I'll see you guys next week.